All right, let's take a look at this problem. This is a classic Atwood's machine. And it's not that hard of a problem, but there are two masses, so we have to be careful. So we look at the masses, or we look at this problem together. It says that two blocks are connected by a string and pulley is shown. Assume the string and the pulley are massless, and the magnitude of the acceleration of each block is what? Well, two blocks, we're going to assume that we have to do Newton's second law for this. And if we're doing Newton's second law, we'd remember that free body diagrams really only work for one object at a time. So I'm going to call this block A, and I'm going to call this block B. So I'm going to look at the free body diagram of A. And it's going to have two forces on it. It's going to have the mass of A times G, my downward weight force because of gravity, and I'm going to have an upward tension force. There's a string pulling up on it. My free body diagram for B is going to be very similar looking. It's going to be a downward weight force of B this time and an upward tension force. And I know because of Newton's third law that this tension force and that tension force are going to be equal to each other. So now I'm going to go back and use Newton's second law. It says the net force is going to give rise to my acceleration. And before I even begin solving this problem, I need to give myself a coordinate system because I need to know what am I considering positive and negative. So I'm going to say that, well, I look at this, 90 grams, 110 grams, this side's going to probably fall. So I'm going to say that up is positive x here. And to be consistent with the string attaching to both of these, so these two masses are going to move up and down together. One will move up as the other one moves down. I'm going to say for my B, positive x is going to be in the downward direction. And I'm allowed to do this as long as I stick to these coordinate systems. All right, so Newton's second law says add up all of our forces. Our forces come from our free body diagram, so I'm going to look at a positive T, positive upward tension force, minus MAG, my downward weight force, is going to give me my mass of A times my acceleration. Similar, when I add up my forces on this side, my x components of my forces give me a positive MBG going in the downward direction, but that's positive for my B object. I have a minus tension force in the upward direction, and this is going to give me MB times A. A, I'm assuming, is positive. It's going to be going down, and it's consistent. This A and that A are the same, because if this one moves up, that one moves down. This moves up a meter per second. This moves down a meter per second. So the accelerations are going to be the same value, and my coordinate system that I chose, the two different coordinate systems, allow me to set both of them to be positive values. All right, let's go ahead and solve this, and we're looking for the acceleration of the block. So if I'm looking for the acceleration of the block, chances are I don't want the tension. So I'm going to look at this equation and say, hey, I have tension over here. That's just equal to MA times A plus MA times G. And now I'm going to substitute this in for this guy over here. So that means I get MB times G minus, inside my parentheses, I'm going to get MA times A plus MA times G. So my mass acceleration, my mass of gravity, and this is going to be equal to MB times A. All right, I'm going to make sure that I substitute this through. I'm going to start joining like terms. I get MBG minus MAG, that term and that term plus the minus sign, is going to give me MB times A plus MA times A. I move my acceleration, or my mass A times A with the minus sign moves to the other side. The minus sign goes away. And I am left with this wonderful equation. So to remember where I am and moving over, I'm going to see that MB minus MA times G, my first two terms, is equal to MB plus MA times A. Well, I don't want MB plus MA, so it's going to be MB plus MA times, or is equal to A. So I look at these, my mass in G, my MA times G, my mass B times A, and my mass A times A. So I'm consistent. This is the classic result for an Atwood machine, and it just involves us now plugging in the numbers. Well, I know that this is a mass term over a mass term. I don't actually have to convert my grams to anything, just as long as my gravity is in the right units. So mass B times mass, or minus mass A, 110 minus 90 is 20 grams. Mass B plus mass A is 90 plus 110 is 200 grams times 9.8 meters per second squared. I will see that this is a factor of 0.1, so I get 0.98 meters per second squared. Choice E, as I have it labeled, is the correct answer. I just solved Newton's second law for one mass, Newton's second law for the other mass, made a substitution in here where this parenthesis got substituted in for our tension here, and just solved the algebra, plugged in the numbers at the very end, and found my final answer.